Hi, I'm Alexander Grosh, and my project is about predicting the spread of the spotted lanternfly using user-reported data. Now, what is a spotted lanternfly? Well, I have an image in the background here. Here's an adult, and here's a recently hatched one. They're plant hoppers, which means they don't fly, and they were introduced from China to the United States in 2014. And since then, they were introduced in like a small area in Pennsylvania, and now have grown to a large range, and they're very destructive. They eat many different types of crops, so they're very economically damaging because they eat grapes, they eat hops, they eat apples, they eat walnuts, and they eat a lot of different types of ornamental trees. And they're costing a lot of money to farmers. And not only that, they're very destructive to the local habitats and they're endangering other species in the area. Here is a map of the range of the spotted lanternfly in the northeastern United States according to iNaturalist. What is iNaturalist? iNaturalist is a website where users can submit photos of plants and animals to its database, along with locations and year of submission. Similarly, here it is according to GBIF. GBIF compiles user observations from many different websites to create a large database of species. As you can see, they're very prominent around eastern Pennsylvania, New Jersey, and say probably northern Maryland. So I made a program to make this map. This map is a current year-by-year range of the spotted lanternfly in the United States from 2017 to 2022. Now, it goes from darkest to lightest. So this little center is the range in 2017, then 2018, 2019, 2020, 2021, and 2022. So this is only over the course of 5 years has it, multiplied in size by many times. So it's spreading very fast. And how did I create this map? I used data points received from iNaturalist and GBIF by sorting them by year, taking the latitude and longitudes of all the submissions. I put them on a scatter plot, and then I made a program to draw a shape around it. And then I overlaid all of these so that I could accurately find the borders each year. And as you can see, they're a little messy, but that's just because how the data points align. There's not really anything I can do about that. Now, what is MaxScent? MaxScent is what I'm going to be using to predict where it's going to spread. It's a research tool that is used to determine the potential habitable land a species can inhabit. It can be helpful in determining where the spotted lanternfly can possibly spread to. Now, what does this mean? It could basically determine which regions are most livable for a species. So it could determine if one region has a good temperature and a good amount of rain for the species, or too much or too little, and it'll show the most habitable regions. So before I input any submission coordinates to MaxScent, I need to filter the data to reduce human population density bias. Since more people live in cities, more submissions come from cities, thus creating disproportionate data. So if I were to give the unfiltered, this is the filtered data set. If I were to give the unfiltered data set, there would be thousands of points in New York City, for example. And it would assume that New York City is the perfect climate for the spotted lanternfly, when in reality, it's just very densely populated. And while it does favor the area around New York City and a lot of densely populated cities, it's not due to human population living there. So having a lot of points from human population, not a good thing. So I created a minimum distance between each point, where as you can see in Manhattan, there's only like 20 or like 15 because I created a minimum threshold that each point has to be away from each other. And that's to reduce population density bias. So how does MaxScent determine habitability? MaxScent makes use of climate variables, which are maps that show climate information about a region. For example, one of which that I used in the prediction was the precipitation of the driest month, or what's the average amount of rain per day in the driest month of the year, which shows how much it rains. Yeah. So here are all 19 that I used. For example, let's take one. Temperature annual range. Difference between the max temperature of the warmest month and the minimum temperature of the coldest month. Or how about annual mean temperature? Daily mean air temperatures averaged over 1 year. So it also continues on the next page. And so these are all very important like climate statistics that'll determine like, oh, maybe it really thrives around water. So annual precipitation high, then it'll live there better. But it depends for every species. So that's why there's so many of these variables. Then once it outputted data, it also outputted a chart of which variables were most significant. So for example, the precipitation of the driest month was a very significant variable on determining where the spotted lanternfly lived. There are quite a few variables that didn't really matter. In reality, only these four like mainly matter for determining where it can live, which shows just how adaptable it is. So here's what it outputted. A map of the potential habitability with 0 on this chart being least habitable, so all the cold and hot areas over here, and 1 being most habitable, which isn't on the map, but that's because nowhere is perfectly habitable for the species. But a lot of where it's spread already is very habitable, but also potentially west is going to be very like dangerous in case it spreads this way. It can cause a lot of damage. So it outputs this in the format of an ASCII file, which can be difficult to interpret. So I made this little chart explaining how to determine like what each of these little things mean. Because this you're supposed to interpret to get this. So it's definitely a little complicated to integrate into a program. But as a proof of concept, I made a prediction of the spotted lanternfly's extent in 2022 using data only up until 2021. And here it is in actuality. And it may seem a little bit off, but it has the general shape pretty much down, where it goes down here, it just fills it in a little bit, and over here on the left, it also just fills it in. And up here, it's pretty stable, and to the east, it's very stable. So I'd say that it works decently well, and maybe it just overestimates a little bit. And now here's the final map that shows the current and the future spreads. So the red here is the same map as earlier, but the green, this darker green is the range in 2023 that it predicts, and the light green is the range in 2024. So it'll potentially expand west very significantly, and the same as in the south. And here is a list of the Python programs that I used, and here is a list of my citations. Thank you.